Well, y'all, we're back with some more classical dynamics, and actually figured out the problem we were working on earlier. So we were trying to figure out the idea of the projection. So the idea from the book is that we have a native or initial uh, reference frame or coordinate system here, and then we alter that coordinate system to a prime frame. We're going to determine the coordinates in the rotated frame. So I rotated the frame 45 degrees for convenience. So theta is 45 degrees, which is this theta here. And I was thinking of what to do about the prime frame coordinates. Well, in this case, since I made the theta equals 45 degrees, so if I was to redraw this, so if we were to, for instance, let this be x and let this be x prime, and our uh, x value, I guess I shouldn't make it get the same color as that axis. This is our x value. So I'll draw an arbitrary length. So this is 6. So this is 6 only along the x-axis. So this same uh, point here, that's what that is right there. And this x prime, I'll make it blue. I just basically rotated I flipped the axis around, and we're taking just these two uh, axes, x and x prime right there. So this is still our theta, which is 45 degrees. And now we want to project this, which in this case, which would be this point here. This point is 6, 0. And we want to project it down here and figure out what this distance is on x prime. So now I made it easy because it's 45 degrees. So pretty much we could just pick any coordinate that's the same. Like we could either randomly pick this to be 2020. But I guess it's going to become more complicated if we have to figure out um, a different angle. So let's try to figure this out with an angle. So we have an angle theta. Well, we know that x dot x prime equals magnitude of x, magnitude of x prime, cosine theta. So I guess I can just arbitrarily pick uh, a magnitude. So we say this is the magnitude 6 because it's literally just the value of that point along the x-axis. And I could just pick a magnitude of 20. But we'll still need the actual angle to get the other side of that, so that's not going to work. So oh, so we know that theta is 45 degrees. So we could just make this a triangle. And we know that cosine of theta equals adjacent over hypotenuse. Thus, adjacent equals hypotenuse cosine of theta, which means that the projection onto x prime of x equals x cosine theta. So that must be how they got that. So this is x prime x1. That is x. Projection of x onto x prime is x1. So basically what we'll be doing is we're calling t x1, x2. So that's going to equal x1 is 6 cosine 45, which is what we had. So that works. And the same thing will happen with the y value. This is y onto x prime. That's why they changed it to cosine. But it should be easy enough because when I have my y value, and we'll call this y, the magnitude of that is 13. And this is still the x prime axis, except now this angle here is 90 degrees minus theta, which also in our case equals 45 degrees. And this reminds me of that's where they got that from. This angle is 90 degrees minus theta, which equals pi over 2 minus theta. Which is going to be the angle of the y to the x-axis. So cosine, so the projection onto x prime of y equals x2 cosine of pi over 2 minus theta, which equals 13 cosine 90 minus 45, which in our case equals 45. It's still 9.19 because sine and cosine is the same at that point. But we know that we need to use 90 minus 45 to make that work out. Oh, which is the same as cosine because of that shift like we did earlier with the sine and cosine. Sine of theta is the same thing as cosine 90 minus theta. Let's look at that. Cosine of that is that the same thing as sine of theta. In this case, we know it is. But I guess we'll need a different angle to test it. So cosine of 20 sine of 20 cosine 90 minus 20. The sine of 20 is the same as cosine of 90 minus 20. If we add pi over 2 and take cosine, it gives us the same value as sine. I'll still have to look at that. All right, so now we know that the projection of y onto x prime and x onto x prime gives us the x prime value. And undoubtedly, the projection of uh, y onto y prime and x onto y prime will give us the projection of project x onto x prime. It seems like it would be 0, and y onto y prime. Well, we'll see if we can figure out the y part of this. Because I can see how the projection of x onto x prime is this. Projection of y onto x prime is this. Add those together, you get that. Put x onto y prime is that. Y onto y prime is this. That is definitely longer than the y value, the y prime value of that coordinate. So let's see. That's 13.44 on x prime. And that'll be what? About 4 or 5 on y prime. It does project. Projection makes a right angle. Oh, well, I see. I would have to actually extend this back here. All right. So the projection, I'll use purple. Projection of x onto y prime is there, which is negative, and the projection of y onto y prime is here, which is positive. So we still have to add those together, and that's why it works out. So let's see how this will work. It'll also be theta. This is a right angle, and this will be 90 minus theta. So for one component of y prime equals x, which is the hypotenuse, cosine 90 minus theta. which is going to be negative, since it's on the negative axis, plus y cosine theta. That's going to equal negative 6 cosine, or in our case, it's still 45, plus two and x2. So negative 13. Hold up. It's still x1. It's just projecting them onto y prime. And x2 cosine theta. So that's negative 6 cosine 45 and 13 cosine 45. So that equals negative 4.24 plus 9.19. That equals 4.95. Yep, and I estimated it will be about 4 or 5. So xp equals x prime 1, 2. So that equals let me finish this one. 0.24, and that equaled up to 13.43. X prime, this is y prime, that equals 13.43, 4.95. X2. Right. Boom, boom. That makes sense. Right, so now we figured out how to get the uh, coordinates in a rotated coordinate system. So, seems like a good place to take a break. See y'all next time.